In setting up any system infrastructure, resources like CPU, RAM, and storage plays a very important role. These components are crucial for the performance and reliability of any system. We will explore each of these in detail. My name is Asadullah Malik and I welcome you to my channel Tech World. Let's get started with the first video of this series. Before diving into the details, it's important to understand how the CPU, RAM, and storage work and are managed. First, data is stored in storage as a program. When the program is opened, it is loaded into RAM and become a process. The CPU then perform computational tasks on it and send the result back. Once the process work is finished, it is saved back to the storage. Now the question is who is managing all this, deciding which program need to be loaded into RAM, require CPU time, or need to be stored in storage. Because if they run independently and directly access resources, the CPU would lack direction for managing processes. RAM management would be difficult. There would be no system to allocate memory to different programs, leading to potential data corruption. File system would not be managed, making it difficult to store, retrieve, and organize data. The operating system is there to manage the CPU, RAM, and storage to ensure that your system operates efficiently. It plays a critical role in coordinating these components to maintain smooth and effective operation. Programs are stored on storage. When user click on a program, for example Word, the OS locates the program files on the storage device and loads them into RAM. It sets up necessary data structure to manage the program as a process. The OS creates the process for application, allocating CPU time and RAM space and schedule it for execution. It ensures CPU execute the necessary instruction to process user input, update the display, and handle other required tasks. The OS continuously manages RAM, ensuring that the Word and any other running program have the necessary memory. It may swap out inactive parts of program to virtual memory to free up RAM for active processes. The OS manages hardware resources, ensuring the CPU, RAM, and storage work together seamlessly. It handles the write operation by transferring updated data from RAM to storage, ensuring documents are saved correctly and securely. This enables user to run multiple programs efficiently and effectively. Now that we understand how they function, let's start with the CPU first. CPU stands for Central Processing Unit. The CPU is the brain of the computer. It is attached to the motherboard and is responsible for executing instructions. Understanding these components is crucial for optimizing server performance and ensuring efficient operation. A CPU socket on the motherboard is a physical connector for a single CPU. Servers often have multiple CPU sockets, allowing for the installation of multiple CPUs on one motherboard. The CPU installed in the motherboard socket executes instructions, runs applications, and handle multiple requests designed for high performance and reliability. Each CPU contains multiple cores that process tasks simultaneously, enhancing system performance and efficiency. These cores are individual processing units within each CPU. Modern server CPUs have many cores, allowing them to handle numerous tasks simultaneously. A thread, often referred to as a software thread or execution thread, it is the smallest unit of execution that a CPU core can handle. A single core can manage two or more threads concurrently, depending on the hardware manufacturer, enhancing the server efficiency and performance. A CPU cycle or clock cycle is the time taken to execute operation like fetching, decoding, executing, and storing an instruction. The speed of these cycles is determined by the CPU clock speed measured in hertz. Modern CPUs have a clock speed in gigahertz, where 1 gigahertz equals 1 billion cycles per second. By looking at the example, this means a single core can execute 2.6 billion cycles per second. Clock cycle can vary in efficiency. Some instructions from one CPU can be completed in a single cycle, while another CPU may take multiple cycles to complete the same instruction. A newer CPU with a lower speed can outperform an older CPU with a higher clock speed due to more efficient architecture. Do not rely on clock speed only to measure efficiency. For overall efficiency, refer to the hardware documentation of specific CPU. In a server environment, cores and thread maximize processing efficiency by executing tasks in parallel. For example, if a core supports a single thread task on that core do not execute in parallel. But if each core has multiple threads, it can handle them simultaneously, distributing the workload evenly and ensuring the server can process a high number of requests at once. That's complete our section for the CPU. Let's jump to our next topic, RAM. RAM stands for random access memory. It's a type of volatile memory used by a system to store data that is being actively used or processed. Unlike your hard drive or SSD, which stores data permanently, RAM is temporary storage that can be accessed quickly by the CPU. Data is available inside the RAM till the system is powered on. When you turn off your system, the data in RAM is lost. Let's see the importance of RAM. As we saw earlier, the CPU works at very high speed. To maintain performance, the CPU requires data and instruction to be executed at these high speeds. Fetching data from RAM is much faster, ensuring that the CPU can operate efficiently without significant delays. If the CPU were to fetch data directly from the hard disk, the latency would drastically slow down processing, leading to poor performance and if inefficiency. The CPU speed is very high, but the disk speed is relatively lower. To optimize performance, we need RAM that matches the speed of the CPU. So, how does RAM work? The data is stored in the storage as a program. All operations are controlled and managed by the operating system as previously saw. When you execute a program such as a Word document, the data and instruction need to run that program are loaded from your hard drive into RAM where it become a process. RAM allows the CPU to access data much faster than from a slower storage drive, acting as a high speed mediator. Once processes are complete, data is saved permanently on storage. Multiple programs run simultaneously as processes inside RAM. Once the process is complete, the data is saved permanently on storage. Now that we have an understanding of RAM and its use, let's look at different type of RAM. In dynamic RAM, data is stored in capacitors and needs to be refreshed regularly because capacitors have leakage issue which can cause the stored information to be lost. It is asynchronous, meaning it does not operate in sync with the CPU clock pulse. When the CPU requires data, DRAM may not be able to provide that information immediately, making it slower. Next is SRAM, which stands for static RAM. It is based on flip-flop circuits where data is stored. SRAM retain its data as long as it is powered on, so it does not need to be refreshed like DRAM. Data is written once and remain until the power is turned off. Storing and reading data is fast, but it requires more power. An example of SRAM usage is cache. The next type is STRAM, which stands for synchronous DRAM. It is synchronized with the clock of the CPU, allowing it to provide data to the CPU at a higher performance data rate when needed. DDR SDRAM is also synchronous SDRAM but with double data rate. Nowadays, when we refer to RAM as DDR4 or DDR5, the double data rate refers to transmitting data on both edges of the clock signal. A single data rate system transmits read and write data only on the upward edge of the clock signal, but what double data rate does is it also uses the downward edge of the clock signal. In this case, the clock signal is used twice on both the upward and downward edges. The size of a single DDR module can be 32 GB, 64 GB, or 128 GB. The quantity of module to be installed in a single system depends on the hardware manufacturer. This is example from one system where we can see all running process on the right. The OS allocates CPU time among these processes, ensuring they receive the processing power they need. It balances the load so that no single process monopolizes the CPU, prioritizing tasks based on their importance and current needs. Memory or RAM is where data and instructions are stored for quick access by the CPU. Each process running on the system is given specific amount of memory. The OS monitor this usage to prevent any process from consuming too much memory, which help maintain optimal system performance. This management ensures that all programs receive enough resources to function correctly without crashing or slowing down the system. We have completed the section on the RAM. Let's jump to our next topic, storage. Storage in a system refer to as the components that store data persistently, such as the operating system, applications, and user data. Unlike RAM, storage retains data even when powered off. The main type of server storages are hard disk drives, SSDs, and NVMe drives, each with distinct characteristics, speeds, and use cases. A hard disk drive is a traditional data storage device used in computers and serves to store and retrieve digital information. It uses magnetic storage to record and retrieve data. Let's check the component inside the hard disk and see how it's function. Data is stored on hard disk platter through the process of magnetic polarization, where magnetic regions on the platter surface represent binary data. The read write heads write data by generating magnetic fields and read data by sensing these magnetic fields. This technology allows hard disks to store large amount of data efficiently and reliably. Spindle is the axis that holds and spins the platter at high speeds, typically 5400 to 7200 rpm, though some high performance drives can spin at 15,000 rpm. Read write head is the tiny magnetic sensor that read and write data to the platters. Each platter surface typically has its own read write head. Actuator arm moves the read write heads across the platters to the correct location to read or write data. Actuator is the motor that moves the actuator arm to position the read write heads precisely. And hard disk installed in a server relies on controller to manage data storage, retrieval, and error correction. The controller translates command from the operating system into precise actions, interact with the computer via bus, and uses communication protocol to ensure efficient and reliable operation. Hard disks are commonly used as primary storage in desktop, laptops, and servers. They also serve as secondary storage when capacity is more important than speed. Additionally, hard disks are favored for data backups and archival due to their large capacities and cost effectiveness. A solid state drive is a fast, reliable, and durable storage device that uses flash memory to store data. With no moving parts, SSDs offer faster read write speeds, improved durability, lower power consumption, and various form factors compared to traditional hard disk drives. They are widely used in consumer electronics, enterprise storage, and embedded systems. SSDs have a limited lifespan due to a finite number of program erase cycles. To mitigate this, the manufacturers uses error correction to recover data from marginal cells, over provisioning to add extra flash capacity for better data management, and specialized firmware algorithm to manage cells efficiently. Inside SSD, there are multiple flash memory chips and a controller chips. Flash memory store the actual data. Each chip contains multiple memory cells where data is stored as electrical charges. The brain of the SSD that manages data storage and retrieval, error correction, and where leveling is the controller. Data from the host system is sent to the SSD via an interface. The SSD controller processes this data and directs it to the appropriate memory cell in the flash memory chips. When reading data, the controller retrieves it from the flash memory cells and send it back to the operating system or host. Starting with SATA SSDs, these have a maximum speed up to 600 MB per second. While they are much faster than traditional hard disk drive, they are limited by the SATA interface legacy design, resulting in higher latency. SATA SSDs are greater for consumer laptops and desktop, providing faster boot times and application loading compared to hard disks. They are also popular in budget servers where cost effectiveness is a priority. SAS SSD improved upon this with speed up to 1200 MB per second and offer enhanced reliability features like dual port operation and error correction. They are commonly used in enterprise server and data centers where reliability and performance are important, but where the highest speed are not necessary. SAS is ideal for RAID configuration that required high availability. Finally, we have NVMe SSDs which utilize the PCIe interface to achieve speed of up to 700 MB per second or more with PCIe Generation 4. NVMe SSDs offer significant lower latency as they are optimized specially for solid state drives. They are perfect for high performance computing tasks, large databases, and virtualization environment where fast access is crucial. NVMe clearly stand out for high demand application while SATA and SAS serve well in more traditional setups. Let's start the topic of NVMe. NVMe technology is a high performance storage protocol that uses non volatile storage media directly connected to the CPU via the PCIe interface using PCIe lanes, typically 4 lanes for a single NVMe SSD, allowing for high data transfer rates. Let's take a look how NVMe technology manages requests. First, the CPU initiates data requests. These requests are sent through the PCIe lanes, typically using 4 link, allowing for high data transfer. The NVMe controller then manages the data flow between the PCIe interface and the storage. The NVMe controller uses multiple command queues to process data. NVMe supports up to 64,000 commands per queue, with 64 queues possible. Finally, the data is stored in NAND flash, the non-volatile memory. This direct connection and high command queue depth allow NVMe to offer significantly higher speed and lower latency compared to traditional storage interface like SATA and SAS, which are designed for slower hard disks. Let's dive into the process step by step. The process began with the CPU initiated a request command. This command is placed into the CPU submission queue, a buffer that holds tasks waiting to be processed. Once the command is read in the CPU submission queue, the CPU uses the doorbell register to notify the NVMe controller. This informs the controller that there is a new task ready to be executed. The NVMe controller retrieves the command from its own submission queue and process it by accessing the NAND flash memory. The controller efficiently locates the user data. After successful retrieving the data, the NVMe controller places the result into its completion queue. This queue holds completed tasks that are ready to be sent back to the CPU. Finally, the CPU checked the completion queue and retrieved the data from the NVMe SSD. The doorbell register is again used to signal that the data transfer is complete, allowing the CPU to continue processing the data. On the left, we have SATA. It has been a standard for connecting storage devices in personal computer. We see three generations here. SATA 1 speeds up to 150 MB per second, SATA 2 300 MB per second, and SATA 3 maxing it out to 600 MB. Despite improvement over the years, SATA single lane architecture limits its speed compared to modern solution. On the right, we have PCIe or peripheral component interconnect express, a high speed interface used for connecting various hardware components including NVMe SSDs and graphic card. PCIe excels with its multi-lane design. PCI Gen 2 offers 500 MB per second lane, Gen 3 double that to 1000 MB, and Generation 4 further increases to 200 MB per lane. PCI support up to 4 lanes for storage, allowing incredible scalability and performance, making it ideal for demanding applications like gaming, videos, artificial intelligence, real-time analytics, and high enterprise workloads. Let's compare these three storage options. Hard disks are best for those on a budget who needs a lot of storage space. Hard disks are affordable and offer high capacity but are slower. SSDs are ideal for general use, offering a good balance of speed and cost. They provide fast speed, durability, and are moderately priced. SATA SSDs are best for small data analytics and light storage applications. NVMe SSDs are perfect for high performance needs, providing the fastest speed and lowest latency. While they offer ultra fast speed and low latency, they come at a higher cost. NVMe SSDs are used for enterprise workload, artificial intelligence, machine learning, real time analytics, and high end systems. We have completed all three sections. Thank you for watching the video. I hope it was helpful. If it was, don't forget to like it. In the upcoming videos, we'll cover networking, operating system, cloud technologies, and virtualization. We'll also cover automation and other tech topics. If you have any question or if anything was unclear in the video, please post them in the comment section and I will try to answer them. Thank you and see you in the next video.